In this new video, I'm explaining the new dispersed system formalism, NDSF for short. It is a formalism, like algebra, for example, that is being used for describing physical systems. And because you can describe it briefly, you can envision new systems that you could not imagine before. It is also very important for scientific research because we need to describe the system in order to order them, to classify, to compare, and so on. So let's look at this first question. What is food? Food, I'm not sure that I like the word food because what I see here is a dish. It's not food. And by the way, there is a confusion between food ingredients and food. Indeed, food is what we eat, as being defined by the dictionary. And food ingredients are not what we eat. So I prefer to have food ingredients and dishes. This dish is clearly organized, and this is what we are going to describe now. First, we use the macroscopic organization. We just describe what we see with our eyes. From top to bottom, we see a sauce, a creamy bowl, a yellow bowl, herbs, and the sauce again. Okay. If we use a microscope to look at any part, we will see something different, of course. And for example, for the sauce, here is the microscopic organization. We see teeny circles with blue rim. Indeed, they are oil droplets dispersed into the orange background. This is an aqueous solution. We say water. In physical chemistry, aqueous solution can be described as water because it's mainly water, and melted fat is called oil. Okay, we see also three air bubbles, the dark circles, but they are an artifact from preparation of the microscopic slide. So now let's look at the various parts of this microscopic using a bigger microscope. And for example, we will be able to see some mesoscopic organization, which means in this case we have casein micelles. They are the size is let's say 100 nanometers, or between 50 and 100 nanometers. There is an organization in these micelles that have been studied even today. And when we look with an even bigger microscope, we would be able to see the supramolecular organization. In this case, it is a complexation. Complexation, we have used raspberries on the left. We have added SN2 plus ions from tin, and suddenly it becomes purple because of the complexation of the tin ions with anthocyanins giving the color of the fruits. Okay, so at any level there is an organization. This is the main point. Now the formalism are very important. Here is a text by Edmond Gobelot, a mathematician at the beginning of the 20th century, and he said very well, if you describe with symbols, then you can produce a lot of formulas, and these formulas sometimes describe something new that you did not envision before yourself. And this idea is based on the formalism by Lavoisier, but also the mathematician at the Renaissance. Lavoisier, in particular, in 1782, created the formal language of chemistry. It is a very important step. Indeed, he was doing what the mathematician did before with Viette, for example, or with Descartes for mathematics. Now, here is the NDSF formalism. We are going to look at it in more details now. It is based on operators, dimensions, and faces. For the explanation, we will not use this order. We will use the faces first, then the operators, and then the dimensions. So let's go. Let's go, but begin with chocolate. Okay, we take a piece of chocolate. Of course, we look at the microscope, and what we see are fat crystals that are making a network, a solid network. Okay. And inside these solid networks, there is some liquid oil, because at a certain temperature, for example, 30 Celsius, part of the fat is melted. And indeed, there is a continuous liquid fat network inside the continuous solid fat network. So you see the description of this system with words, it is possible, but it's quite long. Now, if we consider what appears at the surface of your espresso, people call it a cream, but a cream, for example, for milk, means oil droplets dispersed into water. And this is not what we see under the microscope. What we see is a foam with air bubbles dispersed into water, or water, let's say coffee, but coffee is mainly water. Okay. Now we have to speak correctly, even if we use words. What is a foam? A foam is defined by the Gold Book of UPAC, International Union of Pure and Applied Chemistry. It is online, it is free. My advice, always use UPAC, otherwise you risk mistakes. Now about a plant tissue. This is the microscopic picture of a shallot, a sample of shallots. What we see, we have a solid, the shallot, and inside we have a lot of small bags, the cells of course, containing mostly water. This is a gel formally because it is defined by UPAC, non-fluid colloidal network that is expanded throughout its whole volume by a fluid. It's exactly what we have seen. Now, sometimes it can be more complex. For example, in this picture of potato, we see the starch granule inside the cell. So, of course, it's a gel, but the gel includes a suspension. So we are going to describe this later, but now a more simple system, egg yolk, dispersion of granules in a plasma. When you make a custard, for example, you add sugar, crystals, and you still have a suspension. The solid, the crystals of sugar, are dispersed into the liquid. When you whip, it turns white. Why? Because you introduce a lot of air bubbles. So now you have a foamy suspension. Okay? And finally, when you cook, proteins coagulate, and this is why your custard being thick. Coming back to gels now, remember that we have seen this gel, but meat is a gel as well, because meat is 70% water dispersed into, 70% water dispersed into a solid network made of proteins, 20% plus fat. There is a special organization because the muscular fibers make bundles, and these bundles make super bundles, and you see there is an organization that we need to describe. Now we come back to the simplest gel, gelatin gel. You see in white the protein from collagen making a network, a mesh, and inside you have the water making another mesh, continuous mesh. And as well, cooked eggs, the cooked yolk or cooked white are gels. For some gels, a diffusion is possible. For example, in this picture, you see two gels, gelatin gel, made on the left with 20% gelatin, on the right with 5% gelatin. When the gel was made, some methylene blue was added on top, and you see the diffusion, the slow diffusion from top to bottom, and the velocity depends on the concentration. Let's come back to the question. We have seen many gels, but the word gel cannot apply to all of them, or it applies to all of them, but it is not enough. We want to distinguish the kind of gel. So how to make it? When I was a student, I was introduced to this table. It is not a very good one. It can be useful as a beginning, but we have to go further. In this table, it is proposed to disperse a gas or a liquid or a solid into a gas or liquid or solid. And this is how some words are introduced. For example, gas into liquid, it's a foam, or solid into liquid, it's a suspension. Solid into a gas, it's a solid aerosol. Okay. So this table is not completely wrong, except that you see gel. When you disperse a liquid into a solid, it is said to make a gel. But the word disperse in this case has to be considered very thoroughly, because we have seen with chocolate that it is not a dispersion stricto sensu. So let's move. But remember that we have to formalize, to describe formally such systems. And indeed, with the former table, we can't. So we need the formalism. So we come back to the formalism. We have operators, 5 of them, anti-slash for random dispersion, plus when you have two faces that coexist, included means inclusion, of course, superimposition for sigma, intermeshing or intermixing as you want for X, and then we have dimension D0, D1, D2, D3, and faces, gas, water, oil, and solids. Okay, we need to describe, to fix first a scale for the description. For example, here we have a microscopic picture. We can decide to describe at the microscopic level. For using the NDSF, this idea is very important. Always consider the more important first and the detail later. I take a metaphor. This is a spectrum of coffee, NMR spectrum of nuclear magnetic resonance of coffee. We see one signal, and indeed, coffee is indeed water. So the first order of description is coffee is water. Of course, coffee is not water, but we have to go into more details, which mean we have to multiply the spectrum by 10, for example. And here is what we see. We see more signals, because indeed, coffee is not pure water. Okay. When we have done the job of describing at this level, we can go deeper and see even more signals. So this is the idea that we are going to keep. The most important always first. And for example, for this emulsion, because it's an emulsion, oil dispersed into water, what we see? We have to say first, it is water, W. And then there is a random dispersion, slash, of what? Of oil droplets. Of course, we have to fix some quantities, for example, the size that we consider, and it is added in meters, always the units of the International System of Units. You see, I don't describe the air bubbles, because they are details. Now, this is an emulsion, according to the Gold Book. Okay? And now, with the potato, that was difficult to describe, it's very simple. The potato is a solid, and this solid, we disperse randomly some cells, not exactly randomly, but when we look at with our eyes, we don't see any order. And these cells are made of water, W, into which starch granule, S2, are dispersed. And now the reference size is 10 to the minus 6 meters. Very simple. You just describe what you see at a certain level. Of course, you can add more information, quantities, kinetic, for example, kinetic. With equation, you can describe the making of an emulsion. I'm very fast about that because I don't want to go into this kind of detail now. I want to introduce dimensions. For dimension, it's very simple. Imagine that you have your plate in front of you. You put one seed of rice. It's dimension 0. It's dimension 0 because the size is in is much smaller than the plate, let's say. If you put a spaghetti, it's dimension 1. If you put a sheet of lettuce, it's dimension 2. And if you put a piece of meat, it's dimension 3. So all this has been rigorously defined, but let's keep it simple. Keep this idea at any level. Now, I'm showing you the formula of 3 different dishes. On the left, you have an artificial meat with hollow noodles full of a gelatin gel and glued together with a gelatin gel, exactly as meats, with the collagenic tissue and the inside of the muscular fibers. In the middle, it is an artificial slice of an orange, let's say, and on the right, it is a choucroute. You see, in NDSF, you can describe both the dimension and the face. For example, let's look at this picture that we had before. It's very simple. We have a sheet D2 of a liquid, the sauce, over a D3 of a solid 1, over a D3 of a solid 2, over a D2 of a solid, the herb, over a D2 of a liquid. So you see, very simple. And here it was described with a reference size, which is the plate. Now we come back to the description of the emulsion. D3 water, mainly water. Anti-slash means random dispersion. What do you disperse? Oil, and they are dimension 0. So nothing more simple. You can do it the same with the microscopic micelles or with the complexation. I'm not going into detail, but I want to come back to gels. So this is one kind of gel, D3, the solid, and inside you have a random dispersion of D0 water, the cells. Of course, you can turn it into an artificial gel. This is the same kind of formula. I did not make a D3 but a D2, but imagine that there were more layers, it would be a D3. And they are alginate spheres full of liquid, orange juice, made into a gel. Okay, sometimes it's more complex. Here is the formula. Sometimes there is anisotropy. Anisotropy means it is not the same in all directions. And of course, meat has a direction, the direction of the muscular tissue. And in this case, we have D3, the solid, with random dispersion of D1, the muscular fibers. Sometimes we don't recognize the gel, but it is a gel, as we explained before. We have a D3 solid, the fat crystals, and inside we have another continuous phase, D3, of oil, which is liquid fat. When we have a gelatin gel, we have D3 cross D3, because we have two continuous systems, and it has to be described. Now, we can describe more complex gel. For example, in this picture of a shallot, we see the parenchyma tissue, the cells glued together, but we see also a channel, and the channel is a D1, and the channel is full of water as well. So you see, we describe as a D3 because it is a block, it is a solid, but inside we have the D0 and the D1. For this picture of artificial meat, we have a D3. Inside we have the noodles, and included in the noodles are is a gelatin gel as well. And now we have different formula for different gel, and we are happy because we have no ambiguity. And the question is that we have formula, and remember of Goblet, if we have formula, we can produce formula. And this formula at the bottom was produced by computer, and I asked the computer to produce formula and said, what if we make it as a food? And indeed, it was called the Faraday. This dish was called the Faraday. It is based on this formula, and this is the dish served by Pierre Gagnère. Now, how to use it for scientific research. Let's look at these sauces. They are the French classical sauces, 451. Sauce cardinal, sauce aux champignons, sauce chantilly, sauce béarnaise, and so on. You see, it is messy because we don't recognize any organization. We need to recognize something to understand something. So what science is doing is looking for structure, for that is called laws, but indeed it's structure. Okay. If we use the microscope, we can see that these sauces can be solution, can be emulsion, can be suspension, can be foam, and more. And this is why the NDSF is used. So what I did years ago was to take all the sauces, to make them, to look at the microscope, and to produce a formula. And finally, it appears that only 23 categories are used. They are ordered by more or less the length of the formula in this picture. And I added at the bottom one of the formulas that I did not see in the list of French classical sauces. So it means that you can introduce new sauces based on formula that were not used before. Why only 23 categories? I don't know, of course, but I have a guess. This is the number of sauces in function of time, and you see that the number increased since the Renaissance, more or less. And of course, now with NDSF, you can make any new sauce with any new formula. So now it's in the story. This story is finished. I have to explain about the blue square on the left. It is De Re Coquinaria. It is a book in Latin. Indeed, it was produced probably between 4 centuries before 0 and 0. So it's not. It should not be a square, but an elongated square. Okay. Now, a very important question. You have the formula, the set of formula you can make into physical system, and this physical system have properties. Can we predict the properties from the formula? This is a very important question. I want to show you that it is not pure theory. What we did some years ago was to use a pump, a group of pump, microreactors, and some liquids. And for example, here on the left, you have the microreactor. For example, on the small microreactor at the right, we could blow air and water and get a foam. Or on the left, we could inject oil and water and get an emulsion. So putting these systems in parallel or in line, we can translate a formula at the top into a system, into a physical system. And you can drive everything, the pump, with a computer, and you can make cocktails, you can make dishes. Indeed, in 2003, we produced the Pianoctel. Pianoctel is a system at the core, is a complex microfluidic system, and you can produce 500 billion possibilities. So you see, very powerful. Now, how many gels? This is a question. Remember that we wanted to produce gel, so I made a small computer program, and for the simplest gels, there are a limited number. For more complex gel, you see about more than 1,000 new systems. Here. Okay? The same for suspension. How many suspension? Okay, the same kind of program. Here's the simplest suspension, and now for suspension of class 2, there are 362. It's a different number. You will probably have time to look at Arobase. Arobase is an older version of NDSF. I need to make this new table again using NDSF instead of DSF. The same with slash. At that time, I was using a slash, but today it's an anti-slash, so it is easy to translate, but I need time to make it. And there are other possibilities. Now, all these systems are different bioactivities. For example, on the left, it is the perception that you have when you eat, for example, a pesto that was made by grinding garlic, basil, nuts, olive oil, and Parmesan cheese with a mixer. You get a brilliant green color. Immediately, woof, you have the flavor. On the right, it is the same pesto, but made with a mortar and pestle. And then it is dark green, the color, and the flavor is appearing more slowly but lasts very long. Of course, you can mix both. Can we make a dish with one flavor that would appear, disappear, another that would appear, disappear, and so on and so on? And the answer is yes. If you play with the NDSF formula, you can reach this goal. This is explained in the Handbook of Molecular Gastronomy, a huge book with 3 parts. Part 1, scientific explanation. Part 2, how to use it for teaching. And Part 3, recipes. So you can find all this. I will be happy to answer any question if you send them by email at hervé.tis@inrae.fr. I explained that the picture is Hermes, the Greek god of chemistry, speaking to Bacchus, the Greek god of good food. So finally, celebrate chemistry, and I will be happy to help you further about NDSF.